Now that we've looked at how to find the quartiles, we're going to look at something called interquartile and semi-interquartile range. Both of these have formulas, so we are going to be able to calculate them, and we also need to know what they actually tell us about data. Now, range is something you should already be familiar with from the broad general education. Just a reminder that range is the biggest value in your dataset, take away the smallest value in your dataset. So let's have a look at why, if we already know how to find the range, why it might be useful to find the interquartile or semi-interquartile range instead. So let's take a set of numbers. As you can see here, we have 3, 56, 57, 62, 64 and 65. Now, the range, if I was to calculate that, range is the biggest, take away the smallest, so range is 162. Take away 3, which is 159. Now, the problem with that is, and it's not always a problem, but the problem with that in this case, if you look at the set of numbers in the middle here, they kind of run from 56 to 65. In other words, these are all kind of fairly closely packed. What we have is, at either end of that set of data, we have two outliers, two numbers which are maybe not in line with the other numbers there. And that can quite often be the case with data. You have these kind of random outliers, numbers which aren't really fitting in with what you see with the trend. Something that's massively bigger or massively smaller than the rest of the data is. What the interquartile range and semi-interquartile range will allow us to do is effectively by finding the quartiles, which we can do quickly here. So let's see, we have 1, 2, 3, 4, 5, 6, 7 numbers there. We know that 7 divided by 4 is 1 remainder 3. So 1 number in a box, 3 remainders, which gives us our quartiles of Q1 is 56 and Q3, the upper quartile, is 65. So when I look at that, what that does is, if I take the interquartile range, Q3 take away Q1, it's using these two values here to calculate it, which effectively gets rid of these kind of outlying values. So in this case, the interquartile range would be, let's see, the interquartile range would be 65, take away 56. And the semi-interquartile range, if you look at the formula for that, it's just the interquartile range divided by 2. Remember, when you put semi in front of a word, it generally means half of. Think about semicircle, it just means half a circle. So the semi-interquartile range is just the interquartile range divided by 2. Now, this one here, the semi-interquartile range, is the one that appears in the National 5 specification, so it's the one you're most likely to be asked for. Make sure that you learn these two formulas off by heart. What we're going to do is we're going to go and look at a few examples of finding the interquartile and semi-interquartile range and have a look at what they show us about the data. So in this example here, in part A, we're asked to calculate the median and the semi-interquartile range of the following data set. And the data set here is basically a set of math test percentages. If I want to find the semi-interquartile range, going back to the formula, which was Q3 minus Q1 all over 2, it means I need to know the value of Q1 and Q3. So I also need to find the value of Q2 because I'm asked for the median here. So first thing we're going to do is put all of this data in order and find the quartiles. So the data in order here, it should be, let's see, we're going to have 20, 20, 20, 32, 41, 45, 54, 63, 65, another 65, 79, 82, 95 and 100. And what I'm going to do there, if I want to find the quartiles, I need to know how many pieces of data I have here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pieces of data. So remember, the idea is to take that 14 and split it into 4 equal sections. So dividing that by 4, that gives me 3, the remainder 2. That means each section, each quarter will have 3 pieces of data in it, and I'm going to have 2 numbers left over, which I'm going to have to fit in symmetrically. So 3 pieces of data in the first quarter, then one of my remainders is going to go here, 3 pieces of data in the second quarter, another 3 pieces of data, my second remainder there, and another 3 pieces of data. So what I've got there, as we've shown you before, is I've split the data into 1, 2, 3, 4 equal sections, but I had 2 numbers left over, which I've put in here in these 2 positions. This allows me to quickly write down the quartile. So Q1, the lower quartile, is simply 32. Q2, which is the median value, is going to be halfway between 54 and 63. So remember, if you're unsure, you can just add them together and half it. That's going to come to, in this case, 58.5. And Q3, the upper quartile, is 79. So here we have, in this case, our median value, and we have our lower and upper quartile. So it may be a good idea just to actually write out the median, because that's the wording they use in the question. So median is 58.5, and the semi-interquartile range uses the formula which we gave you on the last slide. So that was Q3 minus Q1, all divided by 2. Remember, this part at the top here is what we call the interquartile range, and it becomes the semi-interquartile range when we divide that value by 2. Now, Q3 take away Q1, that's simply Q3 is here, Q1 is here, so it's 79 take away 32. So it's 79 take away 32 at the top, all divided by 2, and that comes to, let's see, 47 divided by 2, which comes to, let's see, it's going to be 23.5. And that gives us our semi-interquartile range and our median. Now, in part B here, it's asking me, or it's giving me information about another test that the same set of students sat. So in an English test for the same set of students, the median result was 48% and the semi-interquartile range was 16. Make two valid comparisons. What I want to do here is I want to take the median maybe first and compare the 48% median value for the English test with the 58.5% median value for the maths test. Now, median is a type of average, so if we're answering that, we want to use that kind of language. So we would say the median score for maths is higher than for English. And a good way to just compare that is to just in brackets say, let's see, my 58.5 is greater than my 48% for English. Now, what we're doing here when comparing medians, we're comparing average values. So a median is a type of average, so we would use the language, so on average, and that's really important. So on average, the results in the math test were higher. It has a higher median value, so on average, the values in the math test are higher. What is really important here, and I'm just going to say it again, is using this language here. So on average, it doesn't say all of the math test scores are higher, it just says on average. And it's important we use that language within our answer. So on average, that it's a bit of underlined there. It's important that kind of appears in your answer when comparing medians. Now, what semi-interquartile range does is, semi-interquartile range is a measure of spread, how spread out the data is. So if data is very well spread out and very varied, then you would have a high semi-interquartile range. If the data is much more tightly clustered together, much more consistent, then you would have a smaller semi-interquartile range. So the semi-interquartile range is a way of kind of measuring how consistent or how varied a set of data is. So let's make that comparison there. So we're going to say the semi-interquartile range for, let's see which one has the highest semi-interquartile range. So semi-interquartile range for maths was 23.5, and for English the semi-interquartile range was 16. So maths has a higher semi-interquartile range. So we can say the semi-interquartile range for maths is higher than for English. Again, a comparison there, 23.5 is greater than 16. Okay, it's good to compare these things and put in the actual comparison you're making. So the maths results were more varied Okay, remember, a high semi-interquartile range means the data is more spread out. So, in other words, more variation within the data. You could also say that English results were more consistent.